Alrighty, so we are doing right now page 111, chapter 5, which is force and motion. So let's go ahead. If you go to module 5, you should be able to get the PowerPoint. So let me go right ahead. All right, so let's start by defining a force. What's a force? Well, the force is a push or a pull. Now, contact forces arise from physical contact. Now, actually, distant forces do not require contact and include gravity and electrical forces. So basically, a force is any influence of an object that causes an object to be accelerated. Go ahead and write it down. So your force is any influence that can cause an object to be accelerated. What does that mean? How can an object can be accelerated? It means you have unbalanced forces. So an object is accelerated, there's a net force, that means you have unbalanced forces. So we talked about vectors before, and we talked about arrows, and the arrows are used to represent forces. Now the length of the arrow is proportional to the magnitude of the forces. So let's say, for instance, we got an example right over here. Let's say you got two gentlemen that are actually pushing on a block. The question is, which way does the block go, to the left or the right? Well, it depends. If this person over here is getting more force than this person over here, the block will move to the right. If this person over here is exerting more force than the person on the left, the block will go to the left. If they both have exerted the same force, it's an imbalanced force. They both cancel each other. That way, the block would not move. And that brings us to the mass. Now, the mass of a body is a property of matter that manifests itself as inertia. Now, the greater the object's mass, the greater its inertia. Now, the unit for mass is kilogram. The unit for mass is kilogram. Now, so mass is the measurement amount of stuff contained in the object. Now, inertia is the apparent resistance of the object to any change to a state of rest or motion. So let's go ahead and see this video about inertia that we have in the module. So module 5. Okay, there's an inertia movie. So what will Blair do when the air is turned on and shifted side to side? So let's go ahead and see the available answers. Would it move with the track, remain stationary, accelerate in the direction of motion of the track, or accelerate in the opposite direction relative to the track? Go ahead and think about it. Think about your answer. And let's go ahead and turn the other movie on. Which that brings us to Newton's first law of motion. So Newton's first law of motion says, if no net force acts on it, an object at rest remains at rest, and an object in motion remains in motion at a constant velocity. So if an object stays in rest, then an object at rest remains at rest if you have no force on it. That means if you put something on the table or somewhere and you keep it on there, nothing touches it, if you come back next week, next year, next time that place is supposed to be on there where it belongs if there's no net force along on it. And if the object is moving, it keeps on moving unless if you have a force that actually slows it down, accelerate it, or stop it. So an object continues to be in a state of rest or in a state of motion at a constant speed along a straight line unless compelled to change that state by net force. Now the net force is the vector sum of all forces acting on the object. So let's say, for example, let's go back to our little block example with the two gentlemen. Let's say you got one of them going at 10 newtons, the other one is 4 newtons. Where's your net force? Well, it'd be 10 minus 4, 4 newtons to 6 newtons to the right. So the net force of an object is the vector sum of all forces acting on that object. And now the unit of the force is the Newton. Same thing, let's say you have, now you got going up at 3, right to the 4th. So what's your resultant? Again, we talked this about the vector. So your resultant be 4 squared plus 3 squared, square root of that, so you get 5 with an angle of 64 degrees. And we talked about this in the 3rd chapter. Now, inertia is a natural tendency of an object to remain in rest or in motion at a constant speed along a straight line. Now, the mass of an object is a quantitative measure of inertia, and it's actually, again, in kilograms. And that brings us to Newton's second law. Now, Newton's second law of motion states that the net force of an object equals the product of the mass and the acceleration of that object. So let me actually go ahead over here. So we said that Newton's second law, your force is going to equal your mass multiplied by your acceleration. So this is your mass. We talked about it's going to be in kilograms. This is your acceleration, which is your distance over your time squared. Mainly is meters per second squared. And this is your force, and it's going to be in newtons. Now, that means your force, if you talk about in units, what we're going to have? Well, it's going to be, your mass is going to be in kilograms, so it would be kilograms, meters per second squared. Now, your kilograms, meters per second squared, and that's what we call in Newton, we give it a big letter M. So basically, now let's go ahead and watch F equals MA. Let's go ahead and watch a couple of videos to help us with this. And this is the wrong movie. It is. We had the wrong movie up. So in the first movie, if you notice, we have two balls, a green ball and a blue ball. Now, the force on the green ball is twice as that on the force on the blue ball. Now again, because your force is bigger, notice that your acceleration is actually more. So the time for it to actually go the distance for the green ball is actually less than the time for it for the blue ball. So when you have F equals ma, you have bigger force, that means your mass, your acceleration is going to go because both balls are the same mass, so your acceleration is going to go up because your force is going up. Here's our second example. Now this time, both balls again have the same mass, same force, but your masses are different. This time the green mass is twice as much as the blue mass. So notice that your velocity for the blue ball is actually this time bigger. All right. Now, and this is exactly what we just saw. In our first example, the force in one of them is twice as much, which means that the one that had the more force actually went further. The second one, your mass, one of them has twice as much mass. That means the one goes actually, the one that had the smaller mass actually went faster than the one that has double the mass. So your second law, your Newton's second law, again, is your F equals ma, where F is the mass, A is your acceleration, F is your force, M is your mass, and A is your acceleration. F equals ma. And again, we just did this, which is going to be kilogram meters per second squared, which call your Newton. So let's say we have a question. Find the force needed to serve a 60-gram tennis ball at 30 meters per second. The ball is contact with the racket for 0.005 seconds. All right, let's do this example. So your mass is 60 grams. Now let's go ahead and convert it to kilograms. So converting to kilograms, what you get, 0.06 kilograms. What else do you have in the question? You have the tennis ball is going at 30 meters per second. So basically that's your final velocity, which is 30 meters per second. That means your initial velocity is 0 meters per second. And your time was 0.005 seconds. And you need to find your force needed. So your force, now your force equals your mass times acceleration, but we don't have the acceleration. So using the acceleration equation, which is your difference in velocities divided by your time, which is going to be your 30 minus your 0 divided by 0.005. So you get 30 divided by 0.005, which equals to 6,000 meters per second squared. Now we can go ahead, substitute that, and substitute this little fella back over here. What you got? Your force, again, is going to equal to your mass, which is going to be your 0.06 kilograms. Yeah, multiplied by 6,000 meters per second squared. So you should get 1, 2, 6 times 6 is 36. You got 1, 2, 1, 0. newtons. So your force should be around 360 newtons. Now, talking about the weight of an object is the force with which gravity pulls you towards the Earth. Now, your weight is going to equal to your mass times your gravity. Your center of gravity is 9.8 meters per second squared. So, let me go right ahead. You know, we had F equals ma. So when you talk about gravity, your weight, you're talking about W. W equals your mass. Now your acceleration becomes your gravity. So it's your mass times your gravity. So if I tell you what is the weight of a 5 kilogram mass. So your weight is again equals your mass times your gravity, because when you go in, the gravity actually was pulling you down, so it'd be 5 times 9.8. So that's gonna equal to almost, I would say, $49.6 newtons. Now, so let's say you have a block of ice. We'll actually get a block of ice, put it in blue. So this is your block of ice. And it is, let me go ahead, this is stationary. It's not moving. And it has a 5 kilogram mass. Now, on that block of ice, you're gonna have your force going downwards, which is gonna be your weight, which is in this case is gonna be your 5 times 9.8, the one we just got, which you get 49 newtons. Now, opposite of it, the reason that's not moving down, because there's an opposite force that's going on the opposite side. We're going to be calling that your normal force. Now, your normal force is going to be opposite of this weight. So this is going to actually be, again, 49 newtons. So this is going to be negative 49, this is going to be 49, they're going to cancel each other. Now, let's say we have the same block moving at a constant velocity. That means, again, you got your weight going in, down, where your normal force, again, it's the same block, 5 kilograms, so this is your normal force, but then it's going in this side at 5 meters per second. Okay. So according to Newton's law, there is a net force acting on both of them. The first one makes it stationary, where your normal force is canceling with your weight. The second one, you got an extra force that's actually going in, that's pushing it towards the right over here. So your block of ice is providing the counter acting force in the opposite direction. Now, your normal force that we talked about is always perpendicular to the surface area. So your normal force is perpendicular to the surface area. Which means, from the first example, here's your normal force, is going to be perpendicular to this one. Let's say if you have a tilted surface with a block on it, the normal force, again, would be perpendicular to, you got a force is going, let's say you got a block that's going actually downwards. So this is going to be your normal force perpendicular to that area. So mathematically, the net force is written as your sigma x forces. Now, at equilibrium, your sigma forces has to equal to 0, which means all the forces in the x direction has to equal to 0. All your total forces in the y direction has to equal to 0. And then if you have z, all your forces in the z direction must be 0, which we're just going to be doing two dimensions right now. And that brings us to Newton's third law of motion. Actually, we're still on the second law of motion. So an external force acts on the object of mass m, the acceleration that results directly proportional to the net force, and has a magnitude that is inversely proportional to the mass. The direction of the acceleration is the same direction of the net force. So the acceleration, because your again your total forces for F equals ma, that means A is going to equal your sigma forces of F divided by m. So let's say we have a free body. Let's talk about free body diagram for a second. So let's say you have, when I was in college, I was broke, and my car ran out of gas. So I had people to push. So let's say we have two people pushing the car. There's another person pushing the car on that side, right? So let's say the first person pushes the car at 275 newtons. The second person is pushing the car at 395 newtons. Now, the car is actually going on the friction surface. So you got a surface over here on the asphalt, if you will, which means it's actually producing a friction force opposite of the direction. So it's going, I would say, this way. At, let's say, 560 newtons. So if you do that, what's your net force? So your net force is your 275 plus 395 newtons minus your 560 newtons. So it'd be 110 newtons. They actually do it in a graph. So you get a force going in here and a force going in here at 275, 395, and one going this way at 560 newtons. Now let's say they mess with the car. Let's say the car mass now, if your car mass was, let's say, 1850 kilograms, the acceleration, find the acceleration. The acceleration again, your F equals, actually, so F equals ma. That means your A equals all your forces divided by M. Now, all the forces that we had is, again, maybe I should write this down. 275 plus 395 minus 560 divided by your mass, which is 1850. So you get 110 divided by 1850. So you should get 0.059 meters per second squared. And this is exactly the one we got. Okay. So, and again, that's what we talked about, the direction of forces. So all your forces, I should write this down. So your sigma F equals ma, that means all your forces in the y direction equals your mass multiplied by the acceleration in the y direction. All the forces in the x direction equals your mass multiplied by the forces in the x direction. So let's say we have, let's do another example, shall we? Let me just do an example right over here. Now, let's say you got your man on a raft. With the combined mass is 1,300 kilograms. So he is paddling 17 newtons east. When, let me just write that. Now the wind blows with a magnitude of 50 newtons and 67 degrees northeast. Find the acceleration in the y direction and the acceleration in the x direction. All right. All right. So let's go ahead and draw the free body diagram for this one. So let me go ahead and get a blue on this. All right. So he's paddling 17 newtons to the north. Paddling, let's say P for paddling. And then the wind is blowing 15 newtons, okay, an angle of 67 degrees. Now, this 15 newtons, again, is going to be a resultant of your x and the y axis. So this one is going to be, again, your A cosine theta. Let's call this A. Let's say A for air. It's when the air is blowing. So A cosine. Again, this is 67. So A cosine 67. And for this one, it'll be A sine 67. So your forces in your x direction, ignore all the y forces. So in your x direction, what you're going to have? You got your 17 newtons that's blowing in, plus your A cosine theta, which is going to equal to 17 plus 15 cosine 67. So it's going to equal 17 plus, this is almost 7. So you get 23 newtons. Now, your forces in the y direction, on this case, what you're going to be? So for the paddling P, you're only going to have x, you're going to have y. So really it's 0 plus your A sine 67. Which equals to 15 sine 67. So this is going to equal to 14 newtons. That means the acceleration in the x direction, which is your sigma forces in the x direction divided by your mass. Did we define how much the mass was over there? Yeah, 1,300 kilograms. So it should be your 23 divided by your 1,300. And your sigma in the y force is going to sigma y divided by your mass, which is your 14 by your 1,300. So on this one, you get 0.018 meters per second squared. On this one, 0.011 meters per second squared. Now, let's do another example, shall we, on this? So let's say, God forbid, you broke your foot and it's on those one little thingies that's actually the foot is on. Now, so let's say you got tension T1 at 35-degree angle, tension T2 at 35-degree angle, also where your foot's pulling back and a force F. So let's go ahead and do this one. So let's say you got your foot right over here. That's your foot. Go ahead and put the toes over here. All right. So you got, we said that you had a force pulling F on this side, and you got T1 and T2 at 35-degree angles. So you got over here, 5 degrees, T1, you get T2 at 35 degrees. Now, this T1 again is a resultant of T1x and T1y, where again your T1x is going to equal to T cosine, again this is 35 degrees, and your Ty and the y direction is going to be T1 sine 35 degrees. Make sure it's better. T1 sine 35 degrees. And again, same thing for T2, which is going to be, in this case, it's actually going down at, again, a 35-degree angle. So again, this is going to be a resultant of, this is going to be T2 in the y direction, T1 in the x direction. So T2 is going to equal to, it's going negative. So it's really minus T2 because it's going in the negative direction. So it'll be minus T sine 35 degrees, and T1x, that's going to be, or T2x, I'm sorry, T2 cosine 35 degrees. So basically, let me actually draw this better, just to make it a little easier. So you got one going up there, one going down there, T1, T2, and that's your force F. So looking at this, in order to get equilibrium, because your foot is just standing over there, all your forces in the x direction has to equal to 0. Okay, what are the forces in the x directions? Well, this is going to equal to, let's start with T1. So be your T1 in the x direction be cosine 35 plus T2 cosine 35 degrees. Now you also get a F going in the x direction, but it's going in the opposite. So it's going to be minus F is going to equal to 0. Now your forces in the y direction also has to equal to 0. And the force in the y direction, what you got, T1 in the y direction plus T2 is negative, minus T2 in the y direction, which is going to equal to T1 sine 35 degrees minus T2 sine 35 degrees is going to equal to 0. And that's how you set this up. So let's go ahead. We have another question in there. So let's say you got this setup over here where you got the weight is 3150 newtons. You want to find T1 and T2. The first one we just set up the equation. So your weight is 3150 newtons. And you got a car coming out, so this is going to making it 10 degrees, and this is making 80 degrees with T1 and T2. So we're going to actually go ahead and solve this one. So you got this one is 10 degrees with T1. This one is 80 degrees with T2. And of course, you got a force, which is your W, which equals your weight, which equals mg, which is again is 3150 newtons. Now again, let me go right ahead. The T1, that's going to be a convolution of your x and your y component. So for your x component, it's going to be the opposite. So this will be T1 sine 10 degrees. For your y component, it's going to be T1 cosine 10 degrees. For T2, what we got is going down this way. And again, it's a convolution between your x and your y. So this is going to be your T1 sine theta and T2 will be, sorry, that's going to be T2 because this is T2. T2 sine theta, and theta over here is 80 degrees. So your forces in the x direction is going to equal to 0 to have equilibrium. So that means your T2 sine 80 degrees minus, on the first one's going in the negative quadrant, so it'd be T1 sine 10 degrees. We're going to call that equation 1. And your coordinate for f of y equal to 0. That means T1 cosine 10 degrees minus T2 cosine 80 degrees minus, you got your weight going down is going to have to equal to 0. And we're going to call that equation 2. Now taking 1 and solve it for T1, what you're going to have. Actually write this down. This is going to equal to 0. So T1 is going to equal to, sorry. T1 is going to equal to T2 sine 80 divided by sine 10 degrees. Let's call that equation 3. Now we're going to sub equation 3 into equation 2. That means your sine 80 divided by your sine 10, T2 cosine 10 minus T2 cosine 80 minus your work is going to equal to 0. That means your T2 equals your work over, now let's see if we got this right, sine 80 over sine 10, cosine 10 minus your cosine 80. That means your T2 is going to equal to, if you substitute the numbers, (582 newtons), which means that T1 is going to equal to T2, which is 582, sine 80 divided by sine 10. So this is going to equal to 3.3 times 10 to the 3 in newtons. And that's how we solve this to get T1 and T2. Let's check. And this is exactly, yep, we got it correctly. So this is exactly what we've been doing. So after accelerating, it's not in equilibrium. Your force in the x direction is going to equal m mass times acceleration in the x direction. Your force in the y direction equals mass times your acceleration in the y direction. Let's go ahead and do this one last example. The super tanker, the mass is 1.5 times 10 to the 8 kilogram. Is being towed by two tugboats. The tension T1 and T2 is equal to 30 degrees angle with respect to the tanker axis. The engine produces a forward drive of 7.5 times 10 to the 3 newtons with a force, opposing force 40 times 10 to the 3 newtons. If the tank moves forward with an acceleration of 2 times 10 to the negative 3, find T1 and T2. So this is basically what we have. We have your T1 and T2 at 30 degree angles, which are going backwards. So let's go ahead and solve this one. So in this case, we are not in equilibrium. So example, now this is going to be not in equilibrium. Again, let me just write this down. F8 equals MAX, Fy equals MAY. And let me look, yep. So this one, you got a little thing. It's being tugged by T1 at 30 degrees, and this 30 degrees with T2, and you got your opposing R on here. Let me go ahead and do it in a axis. You got T1 along with T2. This is 30 degrees, this is 30 degrees, and this is your R forward. And again, let me do this one more time. T1 is a resultant of your X and your Y. So this is going to be your T1 cosine 30 degrees. This is T1 sine 30 degrees for this one. This is T2 cosine 30 degrees. Again, this is 30. And this is T2 sine 30 degrees. So looking at the forces in the x direction, this is going to equal to your mass times your acceleration in the x direction. So your forces in the x direction in this matter is going to be your T1 cosine 30 plus your T2 cosine 30 degrees we had a forward drive in the question, didn't we? Oh, you have a forward drive and a force rotor, so I forget to put the forward drive. So the forward drive would be D over here. So plus D minus R. That's going to equal to your mass times your acceleration in the x direction. And let's just call this equation 1. Now, looking at the forces in the y direction, which equals to MAY. That means what you got? T1 sine 30 minus, this one's negative, so this actually be negative. T2 sine 30. Your D's and your R, your D and your R are only in the x direction, so you can ignore those. That's gonna equal to 0. And the reason for it, because you're only accelerating in the x direction, you're not accelerating in the y direction when you're on the water. So we can call this equation 2. And again, let me just write this down. The acceleration in the y direction means water. That means your MAY is going to equal to 0. That means in this case, T1 sine 30 is going to equal to T2 sine 30. That means your T1 is going to equal to T2. Let's call that equation 3. So we're going to sub that. We're going to sub equation 3 into equation 1. And by doing so and solving it, what you're going to have, your T so as you get 2t cosine 30 is going to equal to MAX minus D plus R. We're moving these the other side. So that means your tension is going to equal to MAX minus D plus R divided by 2 times cosine your 30. And if we plug that, we should get 1.53 times 10 to the 5th power newtons. Yep, we are good. All right, now that brings us down to Newton's third law of motion. When an object exerts one force on a second object, the second object exerts an equal force in the opposite direction of the first object. For every action, there's an equal and opposite reaction. Equal in force, opposite in direction. So let's say if this whole classroom was made, the whole floor was ice, and you had a table in the middle of the ice. And let's say if you push on the table, what's going to happen? Well, the table, you're going to go backwards. The reason is the table is exerting on you a force the same amount that you exert on the table, but it's in the opposite direction. And because you're on an ice level, there's no friction, so you can actually see the effect. So let's go ahead and see this little video. Notice that each one was the opposite direction of the other one when it stops. So another way of saying Newton's third law is for every action there's an equal opposite reaction. Again, equal in force, opposite in direction. Now the action and reaction forces are always balanced if there's no net force on them. So whenever one body exerts a force on the second body exerts a force directly force of equal magnitude on the first body. And that should conclude chapter 5 for physics 111. If you have any question, go ahead and email me at abunaem@uah.edu, or you can text me or call me at abunaem at 25634848. Thank you.